Hi, I'm Glenn West. This is LLmpager, a project about running mixture of experts language models that are bigger than your graphics card's memory. We take a 30 billion parameter model with 18.5 gigabytes of weights and run it on a 16 gigabyte consumer GPU. It even serves two models at once, with the experts paged in from disk on demand. Here's the plan for the next few minutes. First, an overview of the problem, the idea, and the hardware. Then the source, how the code is organized, and how the key pieces work. Then results, and every number you'll see was actually measured, including the experiments that failed. And finally, the lessons we took away. Everything here is reproducible from the benchmark documents in the repository, and the whole project was built in a single 5-hour session. The problem: mixture of experts models only activate a tiny fraction of themselves for each token. This model touches about 3 billion of its 30 billion parameters at a time. But conventional inference engines still demand that all the weights sit in GPU memory. Our card has 16 gigabytes. The model needs 18.5 before we even talk about the working state. In plain terms, normally, that's game over. You buy a bigger GPU, but per word generated, the model only uses about a tenth of itself. That's the opening. Before going further, a few terms in plain language. A token is a word piece. Tokens per second is basically writing speed. Weights are the billions of learned numbers that are the model. VRAM is the GPU's own fast memory, small but very fast. Mixture of experts means each layer has 128 small specialist networks, and a router picks the best 8 for each token. Quantization stores weights in 4 bits instead of 16, like compressing a photo. Paging is the desk and filing cabinet trick every operating system uses. Keep what you're using on the desk. Fetch the rest when asked. And perplexity is the standard quality score. How surprised the model is by real text. Lower is better, and any damage to the weights shows up in it immediately. Remember that one. It matters later. So here's the idea. Keep the shared core of the model, the parts every token needs, resident in GPU memory. Stream the routed experts from the SSD on demand, and cache the frequently used ones in a per-layer cache. The pipeline runs left to right. The router picks experts. The cache answers instantly for hits. Misses are read from disk into pin memory and copied to the GPU asynchronously. And the expert math runs as soon as its weights land. The trick is that fetching the next folder happens while you're still reading the current one. Before any of this could happen, the hardware fought back. Brand new motherboard, first boot, and the GPU simply vanished. A power management bug wedged it so hard it fell off the PCI bus entirely, and no amount of resetting would bring it back. 2 host reboots, a dive through kernel logs, one obscure VFO parameter buried in a forum thread, and then, 29 minutes after it died, the card came back to life. Line 1 of actual code hadn't even been written yet. Once it was alive, we measured the machine, and those 4 numbers on the right became the speed limits that shaped every design decision. GPU memory, 448 gigabytes a second. The PCI Link 25, the disk 4.3, a motorway, a main road, and a side street. The entire design is about keeping traffic off the side street. The source is about 5,000 lines of Rust and Qt in 5 crates, 5 building blocks. A file format library, the pager that moves weights, a converter that repackages downloaded models in 21 seconds, a runner that generates text, and a web server that answers requests like any AI API. One detail worth noting: nothing here needs the QDA toolkit. Installed at runtime, The GPU kernels are compiled to portable form at build time, and the driver does the rest. It's Apache licensed on GitHub with deb and RPM packages for Debian and Fedora. The expert pack is the on-disk format. Think of it as a carefully organized archive, a header, an index, and then one blob per expert, each sitting at a known position and aligned to disk-friendly 4 kilobyte boundaries. So any expert can be grabbed with one clean read, no unpacking. Weights are quantized to 4 bits in groups of 64, laid out so the GPU can stream them linearly. The models shared core ships as a separate file, which, as you'll see later, is what makes switching models take under a second. The pager is the heart of the system. Think of it as a team of librarians. Each worker owns its own file handle, staging buffer, and GPU stream. When the model asks for 8 experts, whatever's already on the desk is handed over instantly, and the rest arrive from the cabinet in under 2 milliseconds, while the GPU keeps working on something else. Measured on its own, the pager can feed experts at 113 tokens per second, 3 times faster than the compute currently consumes them. Nobody ever stands around waiting. Kernels are the small programs that run on the GPU and do the actual arithmetic, matrix multiplies, normalization, attention, and so on. There are 12 of them, and every single one was verified against a slow but trusted CPU implementation before any optimization happened. Worst disagreement across the whole set about 2 parts per million. That discipline paid off later. Once correctness was established, every performance change could be judged purely on speed, because the output probably didn't change. 3 hours in, at 7 in the evening, the whole chain ran end to end for the first time. The prompt was, the capital of France is, and the model, with its experts streaming off disk through a cache with an 83% hit rate, wrote, Paris. The capital of the United Kingdom is London. The capital of Germany is Berlin. Converter, format, kernels, router, and pager, all agreeing at once. That's the moment this went from an architecture to an engine. Then the performance work, from 20 tokens per second to 41, a bit more than doubled. Each bar is one specific engineering, change vectorized memory loads in the math kernels, releasing cache slots with GPU events instead of stalls, batching all 8 experts into single launches, serving the pack from a RAM tier, and a bit twiddling trick that halves the cost of unpacking 4-bit weights. Nothing here is a bigger GPU or a smaller model. And note the gray bar the pager can still feed 113. The headroom is real. How much cache do you need? We swept it. A bigger cache means more experts on the desk and fewer trips to the filing cabinet, but the curve flattens warm workloads plateau at 48 slots per layer. Cold, varied prompts keep paying for misses no matter what. That observation shaped the roadmap. Stop trying to make misses rarer and make them cheaper instead, which is exactly what came next. This is my favorite result. Perplexity measures how surprised the model is by real text. Lower is better. And it's exquisitely sensitive to any corruption of the weights. We measured it at 2 different cache sizes identical to 4 decimal places. That's the proof that paging is lossless. The cache changes when weights arrive, never what they are. It also priced an experiment we'd rejected, quantizing the core cost for, and 0.5% in quality, on top of being slower. Now we knew both costs with numbers. And then the part that goes beyond the original inspiration, multi-model serving. 230 billion parameter models. A general one and a coding specialist, 37 gigabytes of weights combined, both warm on the 16 gigabyte card, behind a standard OpenAI compatible API. A budgeter divides the cached model running alone, gets the big cache. When a second one warms up, both shrink to share. And loading a model into rotation takes 0.8 seconds, because only its 3 gigabit core actually moves. The experts page themselves in as they're used. Lesson 1 measure. Don't guess. 3 confident, plausible ideas, 3 rejections by data. Quantizing the core to 4 bits should have saved 4x the bandwidth. It was slower because the unpack cost ate the savings. Prefetching the next layer's experts should have hidden latency. It nearly halved throughput because wrong prefetches evict good cache entries and steal disk bandwidth. And more ITO threads made the disk slower, not faster. Best of all, the same core quantization idea wins in one workload and loses in another. Measure the workload you ship. Lesson 2, the memory hierarchy is the product. Bypassing the operating system's file cache is right when the model exceeds RAM, and exactly wrong when it fits. Flipping that one flag was the single biggest win. Allocation granularity silently wasted 60% of our cache memory until an impossible out-of-memory error exposed it. Overlap beat raw bandwidth every time. And caches must age because what's hot drifts. The bottleneck never disappears, it migrates, and only measurement finds where it went. Lesson 3 is about process. Correctness first, every kernel verified before any tuning, which made optimization safe. Prove the ceiling first. We measured what paging could deliver before writing a line of model code. So we always knew where the wall wasn't. And treat negative results as deliverables. The rejected experiments are documented with numbers right next to the wins. The whole ladder paging proof, real tokens, doubling performance, serving multi-model. Went from an empty repository to 10 tagged releases in one evening. What's next? Near term chase the remaining headroom between 41 and 113 tokens per second, smarter cache budgeting, and an 80 billion parameter coding model that normally demands 45 gigabytes of VRAM. Same 3 billion active design, so it should run at the same interactive speed on this card. Longer term, the honest math on trillion parameter models, they fit on our disk and they'd run, but at batch speeds, not chat speeds. The machinery is model agnostic anything mixture of experts with skewed routing pages. If you want to try it, it's one curl command against the server, or one package install on Debian or Fedora, the repository, the full performance journal, and the design docs are all public. I'll leave you with my favorite detail of the whole project, an 18 gigabyte model answering questions about memory paging while its own experts are being paged. Thanks for watching.